There is this question that is just so obvious, so deeply baked into our everyday existence that we almost never bother to ask it.
Right.
And that question is simply this: why does time only flow in one direction?
It really is the ultimate unquestionable fact of reality, isn't it? I mean, you remember yesterday, but you have absolutely no memory of tomorrow.
Exactly. Think about dropping like a delicate wine glass onto a hard tile floor.
Oh, yeah.
It shatters into 100 pieces. And you could just sit there on the floor staring at those pieces and wait until the literal end of the universe, and you'll never see those shards spontaneously leap back up and, reassemble into a perfect unbroken glass in your hand.
Right. Yeah.
Time flows one way, past a future. It's a one-way street.
It feels entirely intuitive to us as human beings living in this macroscopic world. But when you look at the source material we're diving into today, you realize this everyday experience completely masks a genuine mind-bending paradox.
Which is incredibly counterintuitive when you first hear it.
Right. Because almost all the fundamental laws of physics, like the mathematical rules governing how particles move and interact, they work perfectly well in either direction of time.
Okay, give me an example.
Well, if you film two billiard balls rolling across a table and colliding, and then you play that film backward for a physicist, the backward version obeys the exact same laws of motion as the forward version.
Oh, wow.
Yeah, there's absolutely nothing in the underlying physics of those particles or the atomic collisions taking place that says, hey, this is forward and this is backward.
So if the underlying rule book of the universe doesn't actually care about the direction of time, why doesn't reality work in reverse?
That is the big question.
Right. Where does that one-way arrow come from? That is our mission for today's deep dive. We are going to explain the arrow of time for you by unpacking one of the most profound yet heavily misunderstood ideas in all of science.
Yeah, we are talking about entropy.
Entropy.
And entropy carries a lot of baggage as a word. People usually hear it and immediately associate it with, like, disorder or decay.
Okay, let's unpack this. We really need to redefine entropy, stripping away all that scientific jargon and the common misconceptions.
Right, because they can really lead you astray.
Because if you look at older textbooks, they often use this analogy of a teenager's messy bedroom to explain entropy.
Right, the classic messy room.
But that implies there is some invisible, malevolent force out there actively tearing things apart or making a mess of the universe.
Yeah, and the messy bedroom metaphor is highly misleading. I mean, it assumes a human value judgment on what messy even means. We really need a cleaner, more rigorous way to see it.
Okay.
Entropy isn't actually about messiness or decay at all. It's fundamentally about math.
Just math.
Specifically, it's a measure of probability. It is about counting how many microscopic ways you can arrange a system while keeping the same macroscopic appearance.
Okay, so to make this concrete, our sources use a really brilliant analogy. Imagine a brand new deck of playing cards.
A fresh deck.
Yeah, when you first open the box, the deck is in perfect factory order. It's arranged ace through king, grouped perfectly by suit.
Beautifully organized.
Right. And in the entire universe of mathematical possibilities, there's exactly one way for that deck to be in that specific, pristine order.
Just one single microscopic arrangement out of everything possible.
But now, take that deck and give it a thorough shuffle.
Okay.
How many possible arrangements can those 52 cards fall into? The number is staggering.
It really is.
It is roughly 80 unvigintillion.
Which is a ridiculous word.
It is. That is an 80 followed by 67 zeros, a 68-digit number of possible shuffled orders.
What's fascinating here is the underlying mechanism. When you shuffle those cards, why does the deck become disordered?
Right. Why?
It's not because your hands are applying a magical destructive force to the paper. It becomes disordered purely because there is only one way to be perfect, and a mind-bendingly huge number of ways to be mixed up.
So it's just statistical probability. If you pull a random card order from that 68-digit number of possibilities, it's going to look to the human eye like a random, meaningless jumble.
Exactly.
Mess is overwhelmingly more probable simply because there is vastly more of it to land on, like trying to roll 1,000,000 dice and getting all sixes versus just, a random mix of numbers.
Yeah, that's a great way to think about it. And if you prefer a physics example, imagine a single drop of dense black ink gently squeezed into a glass of perfectly still water.
Okay, I can picture that.
Initially, all the ink molecules are clumped together in one tight little sphere right in the center of the water. That is a state of low entropy.
Because there's only a few ways to organize them like that.
Right. There are very few ways for the molecules to arrange themselves and still maintain that tight, perfect spherical shape.
But the water molecules in the glass, they're constantly jittering and bouncing around, right? They bump into the ink molecules.
Exactly. As they bump, the ink molecules drift. And over time, they spread out until the entire glass is just this uniform, pale gray.
Yeah.
So why doesn't the gray water ever spontaneously pull all the ink back into a single dark drop?
Because the odds are just terrible.
Yes, because there are trillions upon trillions of microscopic ways for the ink to be evenly spread out, and only a tiny handful of ways for it to be perfectly clumped together.
So high entropy simply means there are vastly more ways to be like this.
That's the perfect way to summarize it.
The shuffled deck, the gray water, they have high entropy because there are so many microscopic paths to achieve that overall look. The sorted deck, the tight drop of ink, they have low entropy. It really is just a game of astronomical probabilities.
Which brings us to one of the most bulletproof statements in all of science, the second law of thermodynamics.
Okay, here we go.
Now, I know thermodynamics can sound kind of intimidating, but the second law just formalizes the math we just discussed. It states that in any isolated system, meaning a system completely sealed off, where no energy or matter can enter or escape, entropy tends to increase over time.
So things inevitably move from less probable ordered arrangements toward more probable disordered ones.
Not because the universe actively wants to be chaotic,
Right.
simply because the disordered states are so overwhelmingly more numerous that landing in one is a statistical certainty at the macroscopic level.
Let's bring this down to earth with a perfect everyday example from our sources. Think about a cup of hot coffee sitting on a table in an ordinary room.
Ah, a very relatable everyday scenario.
Absolutely. When that coffee is freshly poured, you have a highly specific arrangement of energy because temperature is essentially just a measure of how fast atoms and molecules are moving.
Right.
So in your fresh cup of coffee, you have highly energetic, fast-moving molecules tightly concentrated inside the ceramic cup. Meanwhile, out in the rest of the room, the air molecules are moving much slower.
And in the language of thermodynamics, this is a highly ordered, unusual separation of energy. The fast stuff is all corralled in one tiny area, and the slow stuff is everywhere else.
It's segregated.
Exactly. This is a low entropy state, exactly like the drop of ink before it diffuses.
But if you just leave that coffee alone, we all know what happens. The fast-moving molecules in the coffee are constantly bouncing around. They slam against the ceramic wall of the mug.
Yeah, doing physical work.
Right. That kinetic energy causes the ceramic molecules to vibrate faster, and they, in turn, slam into the slower air molecules hovering right next to the mug.
So they are sharing their kinetic energy through billions of microscopic collisions every fraction of a second.
Just bumping and bumping.
Yeah, and as they share that energy, the fast molecules slow down, and the slow molecules speed up. The heat diffuses until the coffee, the mug, and the room are all the exact same lukewarm temperature. The energy is spread out completely evenly.
Hold on, I have to stop you there.
Okay.
Because we just established the beginning of our deep dive that the fundamental laws of physics are reversible.
They are.
So when a hot coffee molecule hits the mug wall and transfers its momentum, that specific individual collision works perfectly in reverse according to the equations of motion.
The underlying mechanics of the collision are completely time-symmetric.
Yes. So why can't the reverse happen? I mean, if the equations don't have a time direction baked in, saying it's just probability feels almost like a cop-out.
It feels wrong, I know.
It really feels like we're missing a fundamental law. You were telling me there is no hard physical barrier preventing the lukewarm air in my office from spontaneously bumping into my mug in exactly the right sequence to reheat my coffee and leave the room freezing cold.
It sounds totally absurd, but it's true. There is absolutely no underlying law of physics that forbids the room's ambient energy from spontaneously concentrating back into your cup. The laws of motion completely allow for your coffee to reheat itself.
But I have stared at a lot of cold cups of coffee in my life.
Haven't we all?
And not once has one spontaneously started boiling on my desk.
And it never will. This is where probability at the scale of Avogadro's number, the sheer quantity of atoms in a cup of coffee, becomes an ironclad law.
Because the numbers are so big.
Exactly. The number of ways for the energy to be spread out in the room is so unfathomably larger than the number of ways for it to be concentrated in the cup that the odds of the reverse happening are functionally zero.
Wow.
If you waited trillions of times the current age of the universe, you still wouldn't see it happen. The coffee cools for the exact same reason the deck becomes messy when you shuffle it. The math is very incredibly stacked against it that statistical drift becomes indistinguishable from a physical law.
So, what does this all mean for our big mystery? We started out trying to figure out why time only moves forward.
Well, understanding that the cooling coffee is a one-way street of probability brings us right back to our original riddle. This statistical drift is what gives us the arrow of time.
Okay, I see.
The individual laws of physics, the microscopic billiard ball collisions, they don't distinguish past from future. But entropy does.
The future is literally defined as the direction in which entropy is higher.
Exactly.
The future is the direction of more probable, more spread out arrangements of matter and energy. The past is defined as the direction of lower entropy, the more concentrated, ordered states.
The shattered glass on the floor, the diffused ink in the water, the lukewarm coffee on the desk, they define the direction of the future because they represent an increase in entropy.
Okay, so we've established the physical environment, but if I can push this a step further, how does this mathematical probability actually force my psychological reality to experience time moving forward? Like, why do I only remember yesterday?
This raises a really important question, and it takes us right into the biology and physics of the human brain.
Oh, interesting.
Because the two are deeply intertwined. Forming a memory is not some abstract, ethereal concept. It is a physical process. To write information into your brain, your neurons have to change state. They have to pump ions across membranes, forge new synaptic connections, and literally alter their physical structure.
It's like writing a 1 or a 0 onto a computer's hard drive. It requires physical work.
Exactly that. There is this principle in physics known as Landauer's principle, which states that any mathematically irreversible operation like erasing a piece of information or locking a new memory state into place has a minimum thermodynamic cost.
Meaning what, exactly?
It physically requires energy, and in doing so, it generates a tiny bit of heat.
So to write a memory of this conversation into my physical neurons right now, my brain has to expend metabolic energy. My brain physically heats up by some microscopic fraction of a degree.
Yeah, and your skull radiates that heat out into the surrounding room. By generating that heat and releasing it into the wider environment, you are actively increasing the overall entropy of the universe.
That is wild.
The very mechanism of recording the past fundamentally requires dumping heat into the future.
So I physically cannot form a memory without contributing to the universe's drift toward disorder. The arrow of time we experience psychologically is just the arrow of entropy.
Remembering, aging, the fact that a cause always precedes an effect. Every single process that distinguishes before from after rides on the back of entropy climbing. Time, in a very real physical sense, points from order toward mess.
Which is profound, but it naturally forces another massive question. If the universe is a one-way street constantly drifting toward higher entropy, that implies the past had much lower entropy.
It does.
So if you rewind the clock all the way back, why was the universe ordered to begin with?
If we connect this to the bigger picture, it leads us to the very birth of the cosmos. Our universe began 13.8 billion years ago in the Big Bang. And for reasons physicists are still actively debating today, the initial state of the Big Bang was incredibly dense, incredibly hot, and possessed an astonishingly low entropy.
The universe started as the ultimate, pristine, factory-ordered deck of cards.
Beautiful way to put it. And it has been shuffling itself ever since. All the complex phenomena we see today, galaxies forming, stars igniting, planets coalescing, they are just the universe unwinding from that highly concentrated initial state, slowly spreading its energy out across the expanding void.
But when you follow that arrow far enough into the future, it leads somewhere incredibly dark. Physicists in the 19th century were actually the first to grasp this implication, and it remains the ultimate logical endpoint of the second law.
Because if entropy always increases, then everything in the cosmos is essentially running down. The hot stars are radiating their concentrated heat into the freezing vacuum of space. The massive differences in temperature that drive the cosmos are forever being smoothed away.
If you wind that forward far enough, you reach a truly bleak endpoint. A universe where all the stars have burned out, all the black holes have evaporated, and all the energy is perfectly evenly spread out across a massive expanding void.
Just a giant dark equilibrium.
Yeah, where everything is the exact same temperature everywhere.
In physics, this uniform, unchanging equilibrium was christened the heat death of the universe.
Because when everything is the exact same temperature, absolutely nothing interesting can ever happen again.
Right, you need a gradient.
Exactly, to do work, to power an engine, to drive a chemical reaction, or to sustain biological life, you need a gradient. You need a difference in temperature. You need a hot place and a cold place so energy can flow between them.
Without differences, the universe is just a static, featureless soup. Time itself effectively loses its meaning because nothing changes from one moment to the next.
It is the ultimate consequence of probability.
It really is. The heat death is simply the most mathematically likely arrangement of a universe's worth of energy. But to put this into perspective, we are talking about timescales that defy human comprehension.
Right, no need to panic yet.
No, we're talking trillions upon trillions of years into the future. The current 13.8 billion year age of the universe is not even a microscopic fraction of a percent of the time it will take to reach thermodynamic equilibrium.
Okay, so the heat death is an unimaginably distant problem. But here's where it gets really interesting because looking at the world around me right now, I find myself wanting to mount a massive, hopeful counterargument to this whole concept of relentless decay.
Oh, let me guess. You're thinking about biology.
Yes. Look at you and me. Look at the listener going about their day. If the universe is constantly breaking down into a featureless, chaotic soup, how do we explain the complex, highly ordered existence of life? A living organism is exquisitely ordered.
It is arguably the most complex, low-entropy, localized structure we know of in the entire universe.
We build complex, highly structured biological bodies out of simple inputs. Like, think about a towering redwood tree.
Okay.
It starts as a tiny seed, and it builds a massive, structurally perfect, living wooden tower using nothing but thin air, liquid water, and some photons from the sun.
That's incredible.
It is taking chaos and turning it into structure. Aren't living things actively decreasing entropy? Aren't we talking defiances of the second law of thermodynamics?
It is a wonderful observation, and it's the ultimate intuitive pushback against the bleakness of entropy. But the answer is deeply illuminating.
Okay, get me.
To understand it, we have to look closely at the fine print of the rules. Remember the crucial caveat I mentioned when I first defined the second law?
You said it applies to an isolated system, a sealed box where nothing gets in or out.
Yes.
Yeah.
And a living thing is the exact opposite of an isolated system. You are an open system. You interact vigorously with your environment.
I am constantly taking things in and pushing things out.
Exactly. You maintain your beautiful, highly ordered internal state only by constantly absorbing incredibly low entropy energy from the outside. You eat complex carbohydrates and proteins.
Right.
The redwood tree absorbs highly concentrated low entropy sunlight. This is premium structured fuel.
And what do we do with that premium fuel?
Your cellular machinery extracts the energy it needs to maintain your internal structure, prepare your DNA, pump your blood. But the thermodynamic cost of doing all that work is high. Once you've extracted the useful energy, you dump massive amounts of higher entropy waste back into your environment.
We exhale carbon dioxide, we produce physical waste, and most importantly, we radiate body heat.
And that heat you radiate is dissipated, disorganized energy. You are an island of complex order, yes, but you essentially purchase that internal order by acting as an engine of chaos.
Oh.
You increase the entropy of your surroundings far more than you decrease it within your own skin.
So life doesn't violate the second law of thermodynamics. We are spectacular local exceptions funded by a cosmic credit card.
That's a great analogy. When you add up the whole ledger you plus your surrounding environment, the total entropy of the system still goes up, exactly as the mathematical probability demands. Life is actually a spectacularly efficient machine for obeying the second law. We consume concentrated energy and rapidly convert it into dispersed heat.
And the ultimate source funding all of this local order on Earth, the bank issuing that cosmic credit card, is the sun.
The sun is a massive ball of low entropy energy. It pours incredibly concentrated visible light out into the solar system. Life on Earth intercepts a tiny fraction of that pristine flow, uses it to build forests and ecosystems and civilizations, and then the Earth eventually radiates all that energy back out into deep space as diffuse, high-entropy infrared heat.
The universe's books always balance in entropy's favor.
Always.
We are just spectacular little biological machines surfing this massive cosmic wave of energy dispersal.
Yeah.
Let's gather up all these threads for you, the listener, because this has been quite the journey today.
It really has.
We started with the mundane mystery of time flowing in one direction, and we found our answer by fundamentally reframing entropy. Entropy is not some invisible, destructive force of decay. It is simply math.
Just math and probability.
Right. It is the inescapable statistical probability that there are vastly more ways for a system to be mixed up and spread out than there are for it to be highly concentrated and arranged.
And that statistical drift is so incredibly reliable, backed by numbers so unfathomably large, that it governs the physical universe as an ironclad law. Out of that mathematical near certainty comes the direction of time itself.
It is the reason the past is fixed and the future is open. It's the reason the dropped wine glass shatters instead of mending, the reason the ink spreads in the water, and the reason we all get a little bit older, not younger, with every passing day.
I think the most beautiful takeaway from this deep dive is how it changes your perspective on the mundane world around you. The next time you are sitting at your desk and you watch your coffee go cold, you aren't just watching a hot drink equalize with room temperature.
Right, it's so much bigger than that.
You are witnessing the exact same cosmic principle that points the entire universe from its ordered Big Bang past toward its mixed-up, dispersed future. You are watching the arrow of time, one lukewarm cup at a time.
But I want to leave you with one final, slightly provocative thought to mull over, building on what we've unpacked today about human memory and heat. We learned that our brain's physical ability to record the past relies entirely on expelling heat and increasing the universe's disorder.
Right, Landauer's principle.
Exactly. So does that mean our deeply felt conscious experience of time passing isn't actually a fundamental feature of reality? Is it just an artifact of our biological hard drives surfing on a wave of increasing messiness?
That is a deep thought, because if a being existed outside of this thermodynamic drift-like, a theoretical entity whose consciousness wasn't dependent on chemical reactions and entropy generation, how would they experience existence?
Could they experience all of time at once? Past, present, and future laid out simultaneously like a vast static landscape rather than a one-way street. It's a concept that completely bends the mind, and it is exactly why we love doing these deep dives. Remember to keep questioning the obvious things around you. The falling glass, the ticking clock, the cooling coffee.
There's a lot of magic in the ordinary.
Sometimes the most mundane things hold the keys to the most profound cosmic secrets. Thanks for joining us on this deep dive, and we'll catch you next time.